So how do you want to handle questions, Dorina?
So basically, people type questions in the chat, or if you want to address them right away, you can also. I mean, if you opt in for that, because at best you can't actually see the. You can't actually get to see the comments, right?
Right. So maybe, I mean, if you see something that, you know,
yeah, if I see something
right away,
that's
some
very
sort of clarification
urgent
or something, yeah, let me know. And if not, of course, but towards the end we can do the rest. Sounds good.
Okay. And actually, whenever you're ready, just let me know. Wait for.
Yep, I'm good to go whenever you want.
Okay, so well, maybe let's get it started then, shall we? Okay, so hi everyone. So welcome back to this DAGA webinar series. So this is our 14th iterations for this webinar series. And today we're very happy to have Professor Santiago Zagara to give a seminar here. So I guess if you have worked with graph signal processing in the last 3 or 4 years, or 4 to 5 years, you must have heard of Santiago's names. So today is it's our pleasure to have him giving a seminar here. So so a little bit bio about Santiago. So he received his bachelor degrees from ITBA in Argentina, and then his master degrees and PhD degrees from UPenn in Philadelphia in 2014 and 16 respectively. And then from 2016 to 18, he has been a postdoctoral associate with the IDSS of MIT. And since 2018, July, he has been associated with the Rice University as a W.M. Rice Trustee Assistant Professor in the Department of Electrical Engineering, Electrical and Computer Engineering. So his research spans basically the areas of network theories, data science, data analysis, machine learning, and graph signal processing. He received many accolades, such as the 2017 Panzer Joseph and Rosalind Roth Award for the best doctoral dissertations in electrical and systems engineering, and the 2020 IEEE Signal Processing Society Young Over Best Paper Award, and then the 2021 Rice Schools of Engineering Research and Teaching Excellence Award, and many altogether 5 Best Conference Paper Awards. So today he will share with us some of his really cool works on principled simplicial neural networks for trajectory predictions. So the floor is yours, Santiago.
Awesome, thank you. Thanks a lot for the very kind introduction, and thank you to Dorina and all the organizers for the invitation. I'm very excited to be here. Indeed, so today I'll be talking about work with Mitch Roddenberry, one of my senior PhD students, and Nick Glaze, an undergraduate that worked with us. And I'm an assistant professor at Rice ECE. And this summer, I'm also holding a visiting researcher position at MSR, actually currently. I'm there, I'll be there for 2 more months. Good, so how does this talk fit the seminar series? So last year, in December of last year, actually, Michael Schall delivered a talk, Signal Processing on Graph and Complexes, in this same seminar series. So although this talk today is self-contained, one can think of it a little bit as a follow-up to that one, where Michael talked about how can we think of signal processing in simplicial complexes. And today we're going to push that a little bit more and talk about how we think about neural architectures in this kind of data structures. Again, today is going to be completely self-contained, but if you heard that talk, this could be a nice follow-up to that. But we'll be leveraging similar concepts like simplicial complexes, Hodge theory, etc., but in this case for machine learning. Another reason why I'm very happy to give this talk here is that because I had a little bit to do with the inception of this seminar back then. So when this was being built, so this was an email. So we see that Gert here, one of the organizers, was there, and I proposed an acronym DEGA there that it's stuck. So I'm very happy that it's stuck. So I even had this play with the French impressionist painter over there. Of course, Gert, who is the one that could testify to the veracity of this story, has been suspiciously gone AWOL today. So it looks like there's some very high people in important places that don't want the truth to come out. So that's why I redacted everyone else's name. I see some of these people are here today. If not, they will have to put you in a witness protection list or something like so.
We confirm that he is present. News.
I know. Of course, I'm being silly here. But in all truthfulness, so I'm very honored that a lot of important people joined the seminar, and privileged to join that lineup with them. So thanks once more for the invitation. Okay, so enough chit chat and silliness from my end. So let's do a very brief introduction of graph-based machine learning to see what I mean by this. So the idea is to leverage the network structure of the data to improve learning and processing of this data. So let's say that we have a bunch of points here. This could be people. This could be neural regions, and then we have some features assigned to these. If they were to be people, this could be their age, their ethnicity, their geographical location. If these are brain regions, this could be cortical activity of the different brain regions. And then we might have labels for some of these points. In this case, if this could be political inclination, hence the evocative coloring in these nodes. And in supervised learning, let's say the idea would be to try to find a function, maybe a parametric version of that, where we put some x and we get a y, which is a label. And then we're going to use these 5 observations to train that function, or train the parameters of that function. And then once the function is trained, we can use it to find or to estimate labels for person 1 and 7 in here. So what if on top of having these features, we actually have some connectivity structure between them, right? So if these were to be people, maybe we have a social network, and these are some friendship relationships between those. In this case, what we want is indeed to define another function, but this function will be parameterized maybe by some weights, and maybe also by the adjacency matrix of this graph, which is given. And we want to put x and get the label y. And under maybe in social networks, we have homophily, under the assumption that people tend to be friends with people that think similarly to them. That would be an additional piece of evidence to maybe think that this node should be colored blue and this node should be colored red. Of course, in practice, we want to combine the inference or the explanatory power of both the features and the graph structure. And this can be done with something like a graph kernel regression, or more popularly nowadays using graph neural networks. And graph neural networks, and I don't need to say this too much, right? But they have been growing in interest across many different fields, both in theory and in the applied side, because they are a very convenient way of learning when you have irregular domains. And if you surf the web for some headlines, we can see that Google Maps are using graph neural networks to estimate time of arrivals. We have seen that these have been used for quantum chemistry calculations. In the essence of AlphaFold, there is this idea of a graph neural network of permutation equivariance for credit scoring, particle physics, drug discovery, etc. And the reason why these tools are so versatile is because molecules and particles and proteins and urban infrastructure, all these are very irregular structures that can be conveniently represented as graphs. So then we can learn on these. So let me try to make the following point. So why are graph neural networks successful? This is one of the visions, because in a lot of their applications, they're truthful to the symmetries or invariances of the data on which they are being implemented. So to make this point, let me do the analogy with CNNs, with convolutional neural networks. These are nothing more than a sequence of filters, some pooling operations and activation functions, and very much used in computer vision. Well, graph neural networks are just a sequence of local aggregations, these graph convolutions, maybe pooling functions or not, let's say they're not, and some activation functions as well. And then part of the success of CNNs in computer vision have to do with the following, right? So if we use them, for example, for object detection, we're going to detect there's a cat in this image. It really doesn't matter if this cat is in the lower left corner or in the upper right corner. It's just a cat. So the operation of object detection is naturally shift invariant. It doesn't matter where this is. So if this notion of shift invariance is built into the neural architecture, as it is at least partially in CNNs, then CNNs are somewhat learning intuitively on sort of this quotient space of images modulo shifts. So in this case, that we are making it easier for the CNN to learn a cat versus a dog. In the same way, in graph neural networks, we're learning on the quotient space of permutations, right? So it really doesn't matter how we index the different nodes. In this case, two different indexing, we just represent them as different geometric representation of the graph. It only matters, that the yellow node is connected to pink, purple, and gray, yellow node, pink, purple, and gray, and that all the local structures are maintained. So if indeed for our problems, that is usually the case, the indexing is completely irrelevant and arbitrary, we actually want to use a learning architecture that is truthful to this invariance. So in general, enforcing appropriate symmetries in our neural architecture helps with generalization. And this would be design guideline that we will use when we take this into higher order networks in simplicial complexes. So indeed, so far I've been talking about graphs, but those are not the main object of today's presentation, but rather we want to go into higher order interactions. So in terms of structure, again, we want to go beyond pairwise relations. So think of, messaging apps like WhatsApp. Okay, you might have, some chats one-on-one with other people. You also have probably WhatsApp groups where you talk with a lot of people at the same time. Or in co-authorship networks, we have papers that have more than 2 authors. Neuron firing, we have 3 or more neurons firing at the same time. So we want a way to represent this higher order structure. And then we want to think of data that is defined beyond nodes. Okay? So in the motivating example on our first slide, we had information in the nodes, right? So the preference, like the people, age, gender, etc. But we might have information in the edges, in triangles, and so on. And in particular, if we think of information in the edges, then this information could be representing flow of signal, flow of mass, flow of energy between agents. Right? So it could be flow of traffic in a city. It could be flow of birds or people migrating across countries or states in the US. It could be the flow of material in a supply chain, from production to all the way up to the final consumption. So if we focus for 1 second on flows, we'll notice that there are some additional symmetries or invariances to this information. So let's look at this very simple graph over there where we have a flow, this blue flow, where blue represents a flow of +1. So we have this flow represented in the graph. If you think of this other representation where red is a -1, these two are actually different representations of the same entity. There's the same underlying entity with this flow going in one direction. But if we were to represent these, with a vector of +1 or -1, in vector space, they would be different, but they will be representing the same underlying flow entity. So if we want to learn from this kind of data, we have to be aware that these different vector representations will actually represent the same underlying information. It would only depend on some arbitrary orientations of the edges. We actually want to be completely agnostic to that. Or at least just some combination of plus and minus ones in here. Right? All of these, again, are the same flow, but they would be represented differently in terms of vectors. So we want to be faithful to the fact that flows have this skew symmetry. Okay? They should not depend on a chosen orientation, and a flow of +1 in one direction is the same as a flow of -1 in the opposite one. Okay? So this is just something to keep in mind there. So with these ideas, what we have as our agenda, as our menu ahead, we're gonna try to tackle 3 things. First, we want to indeed incorporate higher order relations in our analysis, and for that we're gonna be using simplicial complexes in our modeling. It will be the first point. Once we have that structure defined, then we want to operate on data in these structures, and for that we'll be relying on the Hodge Laplacian. And once we have the structure and some elementary operations to work with data on these structures, we're going to build on top of that to form neural architectures. And with these neural architectures would not be arbitrarily designed, but rather designed with some properties in mind. Okay. So we're going to be tackling these 3 points one by one over the next half an hour or so. So let's start with the first one, probably the easiest one. So how can we encompass these higher order relations? How can we model these? And for this, we're going to be using abstract simplicial complexes, or just simplicial complexes for short. And allow me to do a definition by example over here. So a simplicial complex is nothing more than a set of subsets of another set V that is closed under restriction. So this set V, you can think of it as being the set of nodes or vertices. And then we have subsets of these sets, right? So the singletons will be the nodes themselves. Pairs of them will be edges. Triplets of them would represent triangles. And then being closed under restriction simply means that if this triangle is present in your simplicial complex, then it must be that the edges forming the triangle must be present, and the nodes forming those edges must be present as well. So this is the only thing that closed under restriction means. So the elements of V themselves are again our nodes, so we call those pseudo simplices. The pairs are edges or one simplices. The triplets are triangles or two simplices, and so on. And if we want to define data on these structures, it's just as simple as attaching real numbers or vectors to these different structures. I mean, in graph signals, we just simply attach numbers to the different nodes, here denoted by this color scale. But we could be attaching numbers to the edges, to the triangles, and so on. Right? So this operation is not very sophisticated, but this immediately posits the question: once we have this data defined on these structures, how can we operate on k simplices for arbitrary k? So that brings us to our second point, right? The first one was, as I said, the easiest one and probably the one that we gonna the shortest one. So we'll go to the second point: how can we operate on this data? So for this, let me be a little bit more precise over here. So we're gonna be defining CK as the vector space with oriented k simplices as a basis over your preferred field, like real numbers. So essentially, we'll be attaching real numbers to elements in the oriented k simplices. Notice that C0 are traditional graph signals, so attaching real numbers to oriented nodes. Nodes don't have any orientation, so it's simply assigning numbers to nodes. That's our traditional graph signals. But then in general, C1 would be our signals on edges, C2 will be our signals on triangles, and so on. And once we have these vector spaces defined, we're going to have these maps, del K, these boundary maps, that will take us from one space to another. For example, del 1 will take us from C1 to C0, essentially from signals on edges to signals on nodes. Del 2 will take us from signals on triangles to signals on edges, and so on. And these boundary operators, again, let me not give a very precise definition, but they are essentially what you would expect them to be. So let me define once more by example here. So let's say that you have 3 times the edge 1, 2. Okay, this is an element in this space over here, where we have the oriented edge 1, 2, and the number 3, which lies on our field of reals that is attached to that. Okay, so this is an element in that space over there. If we take the boundary of this, this is nothing more than 3 times the head of that edge minus 3 times the tail. Right? So now we have an element in C0, which is 3 times the node 2 minus 3 times the node 1. Okay, and this is the action of this boundary operator del 1. And this naturally generalizes to higher dimensions as well. This, as you can see, is a linear operator. And then, so we can represent it as a matrix. And the matrix representation of del 1 is the incidence matrix B, which is a very famous and well-used matrix in algebraic graph theory. And we can look at the adjoint of these operators, and those we're going to call a co-boundary operator that essentially goes in the opposite direction. It takes us up this chain of vector spaces. Okay. So with these definitions in place, then we can define the kth Hodge Laplacian, which we're going to denote by delta k. And delta k will be an operator that goes from ck to ck. So from signals in nodes to signals in nodes, from signals in edges to signals in edges, from signals in triangles to signals in triangles, etc. Which is defined, which we build on using the boundary and co-boundary operators that we saw in the previous slide. Okay, so delta k has this specific form. So let me try to drive a little bit what is the intuition behind this form over here. So if we first look at delta 0, right? So going from signals in nodes to signals in nodes, well, in that case, del 0 is actually a zero map, and this becomes del 1 times del 1 transpose, where del 1 is just the incidence matrix. So this is indeed the combinatorial Laplacian that we all know and love. Okay, so then the kth Hodge Laplacian for k equals 0 is nothing more than the plain vanilla Laplacian. What happens when we look at k1? Well, when we look at k equal to 1, now both of these terms matter, let's say. And what are these different terms representing? Right? So remember, delta 1 will be operating between edges. And there are naturally two ways in which two edges can be neighbors of each other. So if we think of a simplicial complex like this one, let's say, where that triangle is filled, okay, so that face, the triplet belongs indeed to our simplicial complex. Then if we look at these two purple edges, these two purple edges are related to each other because they share this common incident purple node over there. So it's a very natural definition. Of course, there's another way in which two edges can be related. For example, these two pink edges, apart from sharing a node, they also belong to this same triangle. Okay, so in that case, these edges are related through the dimension right on top of it. Well, these two different ways of relation are indeed captured by these two different terms over here. The second term goes to the dimension right above and comes down, and this one goes to the dimension right below and comes up. Right? In this case, it would be the relation of edges through nodes through the dimension right below it, and the second one would be the relation between edges through triangles, the relation right above it. Of course, in the case of nodes, there's nothing below it. That's why in the case of nodes, this thing did not exist. But if we look at edges or higher dimensions, we indeed have these two types of relationships between kth order simplices. So that's kind of the intuition behind this operator. And then why this operator, can be useful for learning in general is because, and again, if we think of k equal 1 in terms of flows, there's a very natural decomposition of all of the space of flows that is naturally encoded in the spectral representation of this operator. So let me try to be more precise what I mean by that. So you can define any flow as the sum of constituents in these three orthogonal spaces. One is gradient flows, which are flows that can be defined by gradients defined on the nodes. Harmonic flows, that are conservative flows that go around holes in your space, let's say. And curve flows, which are also kind of these conservative flows, but that go around small patches that are filled with triangles, so filled faces in your space. And these three spaces are very much related to how our Hodge Laplacian is defined. So why is this important? Well, because if on top of this, we're going to try to build learnable architectures that use the Hodge Laplacian as the elementary operation, and we're going to use this to learn from flows, it would be natural that in some applications, maybe gradient flows are more important and harmonic flows are less important, and vice versa in others. So this learning based on top of this operator will be a very natural way to give more weights to one type of flows or others, or to learn how to weight these flows relatively against each other. Okay? So we are essentially building a neural architecture on top of an elementary operator that captures the right structure that we want, in this case, in flows. Okay? So this is kind of at least a high-level idea why building neural networks on this makes sense, apart from them working well, of course. So given that I started talking about building a neural network based on these operators, let's just think. So let's reverse a little bit the usual operation, right? So instead of me defining an architecture in here and then trying to say, this architecture makes sense, let's take the opposite direction and think of a generic simplicial complex network and think what should be natural properties or desirable properties for this neural network to satisfy. So let's think of this neural network in its more generic term. which is some map that go from Cj to Cl, from signals in your edges to signals in your nodes, from signals in your nodes to signals in your triangles, right? So J and L need not be the same. And this will be parameterized by two things. Right? So the boundary operators, which essentially encode the simplicial structure of your data, and some learnable weights W. Okay. So if you recall, back on our first slide with that with that social network, we were saying, okay, we want to learn, some function that is parameterized by theta and A, that we put an X and we get a Y. Well, this is the same thing, right? But instead of having an A that is our adjacency matrix, we got just a bunch of boundary operators to describe all our simplicial complex. And then what we were calling, parameters theta, now we call parameters delta. Okay, so these kind of the same kind of construction, but will take us from signals on the J dimension to signals on the L dimension. Notice that going from C0 to C0 would be akin to a graph neural network. Okay. So I mentioned earlier that we're going to be defining 3 properties that are decidable of these architectures, even before this defining architecture itself. Okay. And these are going to be permutation and orientation equivalence and simplicial awareness. Okay. So this brings us to the third point of this discussion, in which we are going to define these neural networks that satisfy these properties. So let me introduce these 3 properties. The first one, permutation equivalence, we already made reference to this at the beginning. One can indeed define this in very precise terms, but let me try to transmit more of the intuition behind it. So what is the intuition, so we don't get lost in the notation over here? So the idea is the following. Let's say that you have a simplicial neural network, and you put some input in there and you get the output. The output there would be the thing in pink, that pink rectangle. That would be the output of my neural network. So now you grab that same neural network, and what you do is you reindex all your complexes or your simplices, right? And then you also reindex or permute the corresponding inputs. What you should obtain is just a permutation of what you obtained originally. This is this notion of permutation equivalence. So that what comes out of your neural network does not change in essence by the indexing. You just get a reindex version of what you would have gotten if you wouldn't have permuted in the first place. That's the idea of permutation equivalence. And again, this is very much studied in graph neural networks, because even if you don't consider higher order structures, this is of importance in many applications. What does not apply to graph neural network, but applies to simplicial neural networks, is this notion of orientation equivalence, because nodes do not have orientations, but edges and beyond do. So here, remember that small discussion that we had about the skew symmetry of flows, where you can represent the same flow with +1 or -1s depending on the chosen orientation of your edges. Well, you would not want this chosen orientation of your edges, which is essentially arbitrary, to have anything to do with the inference or the explanatory power of the architecture that you're learning. This means that we want architecture to be orientation equivalent. And again, one can define this in precise terms, but instead of getting lost in notation, let me just transmit what the intuition behind here. It's very similar as before. So if we have an initial neural network and we put some input Cj, we get an output. That output is there, the pink rectangle. If what we do is we change orientations in my simplex, and we consistently change the orientations of my outputs, what I should get at the end is just the same output as before, but with the corresponding orientations changed. Okay? So that the underlying, if we're learning flows, the actual flow that we obtain is the same, but we're just changing the basis in which this flow is represented. So, +1s change with to -1s, etc. But everything changes in a consistent manner. Okay? Again, we would like to be learning, if we learn from this, we're learning on the quotient space modulo orientation permutations. And the third of these properties is this idea of simplicial awareness. This one is slightly more tricky. So what we ask of the architecture in here is that it must have the ability, at least, to learn from higher order structures if there is something to be learned. Okay? So let me tell you what I mean by this. Someone can come and say, you know, you're trying to learn a simplicial complex neural network from C0 to C0, let's say. Well, that's just a graph neural network, and I just ignore everything the triangles and out. So you give me a whole simplicial complex, and I say, okay, I just define a graph neural network on the graph skeleton of this simplicial complex, where I ignore all the higher order structures, and I say, this is a valid simplicial complex network. Well, that simplicial complex network would essentially violate this idea of simplicial awareness, which is that it can use information at all the dimensions if it is useful. Something that completely discards everything above edges cannot do that. Okay, so there is a precise way of defining these requirements. Let me not get lost in this precise way, but again, try to drive the intuition behind it. And the idea is that given a simplicial complex network, there exists some outputs and some weighting, okay? Some output and some weighting, such that if the two simplicial complexes differ in some high dimension, then the output is different. And if this is true for every high dimension, for all case, then we're gonna say that the architecture is simplicially aware. So for example, graph neural networks would be simplicially aware up to order 1, because of course, if you change edges, the whole thing changes. But if you change, you know, triangles and so on, these are ignored. So it's not simplicially aware of every order, just up to order 1. And if you want something to be simplicially aware all possible orders, then we just say that is simplicially aware without any further qualifier. Good. So these are the three ideas: permutation equivariance, orientation equivariance, and simplicial awareness. We're going to call these desirable features of this map that we're learning, which is the simplicial complex network. So before providing, you know, an architecture, a simple architecture that satisfies these three properties, let's think about a specific problem that we want to solve. And this problem is that of trajectory prediction. So think of having some agents, maybe a robot that is moving around the room, you know, a person that is moving in the streets of Buenos Aires. So we have, you know, this guy that is moving around. It comes all the way to this point, and we want to predict where he's going to move next. So we want to predict what is going to be the next node that is going to visit, or the nodes that are going to visit in 2 steps, and so on. So this, we can think of it as being given a signal in C1, so a bunch of, so just a flow, which we can represent as a signal on the oriented edges. And the output of that, we want it to be a signal in C0. Kind of what is the next node that is going to visit, or the nodes are going to visit in 2 steps, etc. So we go from oriented 1 chains to a 0 simplex, to a node. And we're going to try to learn this, indeed, by learning a simplicial complex network that go from C1 to C0, given these structures that we have defined. And why do we have, you know, even some confidence that this might work? Is because flows, they're not completely random, right? In this decomposition of a flow into 3 orthogonal spaces that we presented a while back, the kind of natural flows that we observe in many applications, first of all, tend to be conservative. So as much mass as it gains into a point, it tends to leave that point. Of course, you know, there might be noise, there might be losses, and that's not true at the beginning, for example, but tend to be quite conservative in general. And they tend to be crowd-free, right? If you think of a robot moving around the room, they don't tend to move like that just because it's not efficient in terms of energy, right? So this kind of movement is very erratic, right? So they don't tend to move like that, right? So if we have a way to distinguish between the different types of flow, we might be able to learn what is the natural movement of this agent and hence predict where it's going to move next. So we present then SCONE, as in simplicial complex network. Now it's going to be a specific architecture. Before we were talking about a simplicial network in general, now a specific architecture. It's going to be a map from C1 to C0 because we wanted to solve this specific problem. It's going to be a layered architecture, and it's probably kind of simplest architecture one can think of. So here we have the equation of one of those layers, and here we have a block representation of that same equation. Let me tell you what we're doing here. So the input to the Lth layer would be, some signal in your edges. Let's call it C1L. And what we're going to do with this signal is we're gonna mix it. So here we're gonna learn. So these W's are learnable weights. We're gonna, first of all, learn how to combine the elements of this these different features of this signal. And then we're gonna share information across other related edges. And we saw before that related edges could be neighbors in two ways. They could be neighbors because they share a node that's essentially given by this part of the Hodge Laplacian. And then we also learn a way to mix the features in there, or because they are part of the same triangle. And we also, mix the features with some learnable weights. We pass that through a nonlinearity and we repeat. In terms of a block representation, essentially we are here in edge space. Then we have some operation that remains in edge space, which is that one over there. One that takes us to triangle space and back, which is this one over here. And one that takes us to node space and up, which is that one over there. We just sum all of those, pass through a point with nonlinearity, and we get the input into the next layer. We repeat this operation for capital L layers. Once we have a capital L of those layers, we still have a signal in edge space. So then we simply project it into node space using our boundary operations, which are these elementary ways of moving from one space to the other. Again, with some learnable weights that can mix features as well there. And then as a final operation, if we actually have a subset of node candidates on which we want to do the inference, we essentially restrict this guy to that subset of nodes and do a softmax, and that will be the output of what is the next node in our trajectory. So this is, again, one reasonable way of defining a neural architecture given what we've been talking over the past 37 minutes, right? Defining the Hodge Laplacian, etc. This is a very natural way of defining architecture. But now an important question is, does this architecture satisfy the three properties, which are permutation equivalence, orientation equivalence, and simplicial awareness, that we mentioned that they are kind of natural desirable properties for this kind of mapping? So then we have the following result, which says the following. So if we assume that this activation function phi is continuous and element-wise, as usual activation functions are, if cone is admissible, and admissible here means satisfies those three properties that I mentioned, then this phi must be odd and nonlinear. So this is kind of nice, right? Because it gives us design guidelines for this activation based on these principles that we've defined. On the one hand, phi must be nonlinear. It means that here we cannot have a linear activation function. It means that we need to go beyond essentially filters defined, which are linear operations, filters defined on these simplicial complexes. Here we have a linear activation function, and we stack a bunch of layers. We're simply having kind of the analogous of defining a filter in a Hodge Laplacian. And we see that if you actually define a filter in a Hodge Laplacian for this task here, that would actually violate simplicial awareness. We can discuss why that is the case if anyone is interested. So on the one hand, it has to be nonlinear. On the other hand, it has to be odd. Okay? So this again is theoretical guidance on the design of this architecture, which is kind of nice. In particular, since phi has to be odd, then we're going to define that to be tanh, so hyperbolic tangent. Right? So instead of choosing ReLU or leaky ReLU, just because it kind of works well on other domains like computer vision, here we try to have a more principled decision on the selection of your nonlinearity. And again, if you wanted to satisfy those three properties, essentially, if you accept those three properties as reasonable, then the nonlinearity must be odd. And we hope for this to promote high performance and generalizability, as we'll see in some examples next. So let's get to that. Okay, so here we're gonna try to solve the following trajectory prediction task. We have this space over here. We have triangulated this space. This space has these two holes essentially. We have nodes, we have edges, and all the purple faces are filled in triangles. And then we have three types of trajectories that were observed, right? The ones that go above the hole, between the holes, and below this hole. So we actually observe these trajectories. How are we generating these trajectories? Well, we select a node at random from here. If we want to generate a trajectory of the first type, then we select a node at random from here, and then a node at random from there, and then we join them through shortest paths. So then we generate a bunch of these different trajectories, and we do the same for nodes in these 5 different portions of the simplicial complex to generate these 3 different types of flows. And then during testing, we get to observe, it's kind of a mess, I should erase that. During testing, we get to only partially observe some of these flows. Right? For example, we observe a flow all the way up to here, and then we need to determine where is it going to go next. This is the task, very clear and well-defined task. So what are we going to compare us with? Okay, so we're going to compare us with a simple, Markov inference methods, where essentially memorizes when you were at a given point, what is the next most probable point to go given your training data. And RNN architecture is very sequential in nature, so we can indeed fix an RNN that is completely myopic to the underlying data structure of the simplicial complex. We could do essentially projections into the kernel of delta 1 or del 1, which is projecting into the harmonic space, either considering triangles or, in the case of del 1, essentially not considering triangles or ignoring the triangles. And then we have this scone architecture that we talked about. The scone with tanh, this is actually what we were proposing based on our admissibility criterion. And then we have scone with tanh, but ignoring triangles, and then scone with 2 other activation functions. Okay, so these are the kind of things that we're going to compare in this task that we just defined. So if we look at the performance, which comes next, so the larger number, the better. And when you obtain something like this is kind of anticlimactic, right? Because I spent 42 minutes trying to convince you that simplicial neural networks are a good idea, and then along comes this RNN and gets better performance than that scone over there. Right? Of course, this is not the end of the talk. We still have 18 more minutes, so let me convince you that this still makes sense. So the design principles behind this scone, what we said is we hope them to help us in generalization. So maybe, in this case, RNN might be memorizing very well, but might not generalize well. So what do I mean by this? Okay, let's look at these 2 other tasks that we have here on the right. The first one, rev, meaning reverse. In this case, what we said is, let's have the same training data set as before, but now during testing, what you're observing are actually flows in the opposite direction. Okay. It's kind of, you're not changing much, it's just the same kind of flow, but going in the opposite direction. There you can imagine, like something like Markov and RNN would fail miserably, right? Because they never seen a flow in the opposite direction, right? So they have no way to reason out from this way. But scone can generalize well, again, because it's kind of learning this base of flows, right? And then you observe a partial flow in the opposite direction. So you use the same basis, but now you give an opposite direction to the real number, to the field that you have. So then you can generalize well in the opposite direction too. So that's kind of a nice feature of this kind of architecture. And then in terms of transferability, what we did was the following, right? So with the same idea that graph neural networks have this inductive learning, that you can learn on some parts of the graph and then apply it on some other parts of the graph. Well, what we did is the following. So we've trained essentially with these 2 types of flows, okay? And we've never observed the 3rd type. And then during testing, we wanted to predict what was the next step on a flow of the 3rd type that was never observed during training at all. Okay? So in a case like this, then this Markov and this RNN case cannot do anything more than just random, right? Because they just take a sequence of nodes And they've never seen these nodes at all during training, so they have no idea where to go next. But again, something like SCON, what we're proposing over here, can generalize well and transfer well to parts of these simplicial complex that were not observed during training. Okay? So this is what we wanted to emphasize on this specific experiment. So to have a little bit more of this discussion of why tanh actually makes sense, once more, we can do the following experiment. So in terms of the standard experiment, they all of them seem to work very, very similarly. But if we do the following, if we actually orient every edge based on the XY coordinates of their corresponding nodes, so that the orientations go in this northeast direction, right? So the actual orientations of most of the edges are like that. Since our flows kind of go in that direction as well, most of the flows will be represented with positive values. Again, the choice of the orientation is completely arbitrary, so we are choosing the orientation. The flows are given, and since they go kind of in the same direction, they will be represented with positive values. Now, if we run this reverse experiment that we said before, where we during training observe flows in that direction, and then during testing we observe a pink flow, then if you're using something like Red or sigmoid, then you're dead, right? Because during training you observe a lot of positive values, and almost no negative value. And then during testing, you want to output a negative value, but then your activation function has not learned this thing, and then cannot really generalize well. Whereas this odd function, which is tanh, again, the whole architecture is kind of odd, right? So outputting a 1 or a +1 is you just change something in the input, you just get that thing changed in the output. So it's kind of natural for this case to generalize in that respect. So it's good because we are somewhat myopic to these arbitrary orientation choices you probably want to be. We also run this on some real world data. So let me show you that. So it's Madagascar and Berlin. So these are the two data sets. So here on the left, we have the island of Madagascar in the east of Africa. And there we have buoy data, actual recorded buoy data that go through the ocean around Madagascar. So we can model the ocean with this triangulation where the whole is naturally the island, right? So there's no buoy on the land. And then we have these buoys moving around. Okay? And we simply do trajectory prediction just like we did before, okay? By using this architecture. Also, we did this in the city of Berlin, where we have a map of Berlin, and then we have trajectory of people walking around it. In this case, the people themselves are synthetic, or just kind of shortest path in the map. But the nice thing here is that it's very natural to represent a map with rectangular cells as opposed to triangular cells. And everything that we discussed today very, very naturally extends to general cell complexes as opposed to only simplicial complexes. There could be rectangular complexes as well, as we illustrated in this specific experiment in the paper. And then if you run this for the ocean, essentially the Madagascar and then Berlin, and you compare this with some old suspects that we already seen in the previous slide, and some other additional ways of defining these simplicial complexes, but some by people at EPFL, for example, then here we actually observe a better generalization just because this is driven by these principles that we mentioned before. And in particular, the choice of the odd nonlinearity helps us in generalizing in this case. So again, it's kind of nice that we have a theoretical framework to guide the design. And we see that, at least in the cases that we've seen, this indeed translates to better generalization in practice. So with that, here, a lot of related work on this area. It's kind of a hot topic I'm picking up now. So this is the paper that I talked about today. Of course, the presentation has been highly biased with what we did in my group. That would make sense. And then we also had this other paper with Mitch back in Asilomar 2019, which I think was the first, or if not one of the first uses of Hodge Laplacian in neural networks. And then there's a lot of very interesting work in this area. So if you're interested, I do recommend you to look at the broader literature. So these are the two papers that I mentioned in the previous slide. Then the paper by Michael Bronstein and others who also talked in this seminar. We have some people. So a paper by Vince Poor and collaborators, by Elvin and Gert. Mustafa has also a lot of work in here, by Sergio Barbarossa and other collaborators, etc. A testament to how hot this thing is that there are these two papers that were published on arXiv like a month apart from each other, and they're called Simplicial Attention Neural Networks and Simplicial Attention Networks, by two different groups, and of course doing attention mechanism on higher order neural networks. So indeed, people are working on these topics and kind of extending and expanding this theory in many interesting ways. So I recommend you to check all of these out, and probably many others, right? So this is not exhaustive in any way. So to conclude, so we can have 10 minutes for discussion. So a key element of graph neural networks is permutation equivalence. And in general, methods that respect the invariance of the underlying data can transfer and scale well. This is kind of the leitmotif or the driving reasoning behind what we developed here. So we added these other properties based on that driving principle: orientation equivariance and simplicial awareness. And then we talked about admissible neural networks, which are the ones that satisfy these three, and we showed that admissibility require specific choices on the activation function. And this led to better generalizability in practice. So with that, I conclude. Thanks a lot. This again is the reference for this paper. I'll be happy to take any questions. Thank you.
Right. So thanks, Santi, for the very nice presentation. So I think I will start with the questions that are already on the chat. So the first one actually asks for like when we define the so when we are defining the Hodge Laplacians and the higher order operators, is it possible to use adjacency matrices instead of Laplacians?
Yeah, so that's a good point, right? So this, indeed, these local operations, one can even think of them, even if in a more generic case, kind of as a message passing operation with whatever other k-simplex is adjacent to you, right? And you can define this adjacency indeed. They are what you would lose, and this I see it a little bit like the relation between the more general message passing representation of graph neural networks and kind of a more signal processing way to think about these operations. Here I see a similar dichotomy, right? So the Hodge Laplacian again gives you this natural way of then you think in the spectrum of the Hodge Laplacian, and you have this decomposition of the flows. So it's kind of nice, right? And you can reason about it. That being said, indeed, by looking at adjacency matrices or even message passing operations within adjacent k-simplices and putting learning in there, you could be able to get more expressive architectures. So indeed, I think it's worth exploring. There's always kind of this trade-off between what intuitions you can gain and then what performance you can get on a specific problem.
So thanks. I think that actually addressed at least my concerns about this. Like I have the same question myself also. So the next question has the following thing. So it says that like in a chain of data that is something like time series, such as like time t is connected to t-1 usually. So in which kind do the triangles or the more so for this kind of data, for this kind of chain of data, so do you foresee the emergences of things like triangles or some more complex shapes that you describe in your work?
Yeah. So notice that even if you don't have the data defined on the triangle, having the triangles as part of your structure can help in learning, right? So and that's what I mean by like in this case of the island, right? So the data that we get are indeed trajectories, and these trajectories indeed move in continuous space, right? So in physical space, they cannot just teleport from one place to the other. I agree, and so you move through these edges. But the fact that you have triangles in here and you have this hole in there gives you additional information that you would not see if you just look at this as a graph and you just don't have any triangles at all. Okay? So you need not have data on the triangles for them to be useful, but you could have data on the edges, and then knowing that some parts, let's say, of the space are filled in and some parts are not. So they have some, again, obstacles in some parts and not obstacles in others, can help in your inference. And that's where I see it being most helpful.
So the last question before I move on to the live questions. So there's one more question about, like, can you try to explain intuitively why does the tanh function makes more sense than the ReLU function or the sigmoid?
Yeah, certainly. Right. So so there it goes all the way. Maybe if we go back to so to this representation, right? So imagine that we're here and we're trying to solve the problem that we end up solving at the end of this trajectory prediction, right? And then your trajectory might be, the blue one, and you're here and you want to say where are you gonna go next? Right? So here, the thing that you input into your neural network will be a bunch of +1s, right? Because the movement is in line with the chosen orientation. Right? And then, you operate on this thing, and then you pass it through your first nonlinearity in the first layer of it. Right? If this nonlinearity is not odd, right, it will essentially treat different this guy from that guy. It will be treated different, right? Because what you learn in the first layer is not going to transform one to the other, already, right? So it's going to be treated different. So for that neural architecture, these two inputs would indeed be kind of different, right? And then for both of these two inputs, you will have to separately learn what is the next point in your trajectory. Whereas actually they are the same trajectory. So if you learn a good point for the blue one, you also get a good point for the red one. And something that has odd activation functions will indeed learn kind of, again, that quotient space of orientations.
Yeah, that makes sense. So I guess it's time for some live questions, and I saw Gonzalo's raising his hand for quite a while, so please.
Yeah, thank you. Hi, Santi, thanks for the talk. I was curious in your comparisons at the end, those baselines, those 2020 papers, the SCNN and what have you. What are those architectures kind of missing so that they perform worse? I understood the other baselines, they're intuitive, but these ones I don't know. It's basically just activation function or something else?
That's a good point. Yeah, I would say that the main difference is on the choice of the activation. I would say that at least is the main difference that we wanted to emphasize in here. I mean, there might be other small differences, and that might be escaping right now, but at least what we saw to be the main driver of the difference in generalization was that. Yes.
So that could be in your previous comparisons, you had your scone with some other like even or whatever. That could be kind of similar to these ones, maybe somewhat.
Yeah. So here, yes, indeed, right. So here, what I think is an interesting output of the talk and of the paper. I mean, I wouldn't say scone itself to be the architecture itself to be the main value of the study that we're trying to do here, but rather this framework to think about this kind of architecture, right? So some of these other papers like Elvin and Hert with Young, they worked on architecture, similar to scone, but instead of having kind of a first order polynomial in each layer, kind of higher order polynomials of the Hodge Laplacian in those cases, which of course have more expressive power, and it's very useful in practice. And then you can indeed show and think, is this orientation equivariance or not? There, of course, you also require odd nonlinearities, etc. So I would say more of this framework to think about this kind of architectures. I see it more as the value than the specific scone architecture that we use just to illustrate this framework.
Good, thank you.
Mm-hmm. Yeah. So I guess next up we have Professor Yanakis. So can you unmute?
Oh, great. I can even, all right. As always, excellent line of work, Santiago, and at least as great delivery. I cannot claim I understood the depth of Hodge Laplacian and its implications, but I will stick to one question that crossed my mind. You mentioned that you want to capture higher order relationships.
Yes.
That's your first objective. And in my mind comes this notion of correlations. So instead of second order correlations, you are trying to capture also third order correlations.
Right.
And eventually, if you use as many correlations, you can approach any probability density function. Any. Okay. So why do you claim that the Hodge Laplacian would be a better tool than, let's say, triple correlations?
Yeah.
Or intuitively, do your approaches translate to utilizing triple correlations through your triangles?
Yeah. So that's a great question. Thanks. And we know that your higher statistics background, of course, is very much appreciated here, right? So so I would say that in the examples that we used over here, these simplicial complex or cell complexes in general are actually being used to represent the substrates on which the data is defined that goes beyond the data itself, right? So this is not inferred from the data, like that you have the island of Madagascar there, or you have a building in Berlin, right? So this is not correlation information that is inferred from the data, but rather additional information from the domain that can be used to infer something. So in those cases, I would say that we were claiming Hodge Laplacian to be useful. You can infer these domains. One thing that we're looking at is kind of trying to infer holes where these holes are not naturally present in there, right? So that the island, of course, you cannot have a buoy in there, but just because of the movement of the ocean, there might be kind of also a hole in there, kind of a virtual hole, that buoys don't tend to go in there. Just from all your historical data, there's kind of a hole in there that they don't tend to go there. So if you are able to identify that hole, that can help in future inference naturally. So these are the kind of higher order information that we would think that if you incorporate it in the Laplacian might help. And this could be complementary to the understanding of higher order correlations.
I see. Yeah. Thank you.
No, thank you.
So I think we have one more question from Sherlock. So can you please unmute?
Yes, hi. Thank you very much for a very nice presentation. I have a question regarding the nonlinearity that you used there. You had these two properties that it had to be odd, and also it has to be
it has to be nonlinear.
Nonlinear, right?
Yes.
But there is a large number of functions that satisfy those, and you ended up using tan H.
Yes.
So is there any intrinsic property in tan H that you want to explore, or you can have other functions also input there? And if for example, if I change it, what kind of relationship I might get at, or the performance I could get at the end? Yeah.
So thanks. Yeah, thanks for the question. So this is so we tried to gain a little bit of intuition on that. So let me maybe spend a minute in this. So in tan H, right? So we said that this thing has to be nonlinear in general, right? Then okay, that's a terrible, but let's go through the origin of that. We said that it has to be nonlinear in order to get information from higher orders. The reason for the nonlinearity part, and I'll go to the odd in a second. The reason for the nonlinearity part is that if this were to be linear, then here, if you don't have a nonlinearity, if you apply two layers of this, we have that the boundary of a boundary is 0, just in like how homology is defined, right? So then if you want information in your nodes, you cannot percolate information from your triangles, because you have to apply boundary twice to get there, and you've killed information. So you have to put nonlinearities in the middle for this information to survive, let's say, successive boundary operations. Now, if you have a nonlinearity like this one, that is kind of linear in a part of it, and then it's nonlinear, since you're actually learning these weights over here, you can learn a scale where the neural architecture can actually make things look like linear if it wants to say something about homology type of things. And then it can go all the way to the nonlinear case if you actually want that information to percolate. So this was our intuition of why this is kind of nice, but we haven't gotten anything formal out of it. That would be my answer to the question.
So basically, linearity at the origin is the important factor here. Also, it's a third useful property that you can add there, right?
Yeah, this one, let's say, less formal than the others, so no proof in there, but at least from a user perspective, we think that might be playing an interesting role. Yes.
Thank you.
Yeah, you're welcome.
Also, actually, I do have a follow-up on this. So my understanding about the statement right here is that this odd and nonlinearity is only a necessary condition, is it? So it's only a necessary conditions for the admissibility conditions, right?
Right. So it's if it is admissible, so first of all, this is fixed, right? So we're fixing it to be continuous and element-wise, right? So we are not looking phi outside of that, right? So then we look at the specific subset of phi's that are continuous and applied element-wise, right? Then if scone is admissible, then this must be true, right? So it is indeed necessary for this to be true. Agreed. Yeah, 100%.
But not sufficient, right?
It's not sufficient. That's a good point. Yeah, it's not sufficient. That's a good point. Yeah, you can make, indeed, right? You can make something that maybe destroys information from higher orders or something like that, and then it would not be simplicial aware. But it has to be these things. Exactly. That's a good point. Yeah, that's a good point. Okay. But hyperbolic tangent satisfies sufficiency as well. So it satisfies these things. Yes.
Okay.
Yes.
That's good. I think we have just one last question in the chat right now. So it asks like what type of data can be leveraged for trajectory prediction under the current framework. Like, for example, do you foresee any applications in the wireless networks?
Yeah, so here, and this is actually related to the first question of all, right? So, when the data actually has to do with flows, and this could be flows of packets in a wireless network, then these things tend to be useful and work well. A lot of times you might have data on the edges that are not flows. They're just some edge features, right? You want to do edge classification, right? So you have labels in the edges or edge regression. You have, capacity of the edges or something, and you go and trying to predict the capacity of another edge that you haven't observed. In those cases, things that are maybe more based on message passing, or even more based on correlations, on higher order correlations, as was mentioned by Professor Janakis, those could be nicer, right? Because they are the flow interpretation of this harmonic and gradient flows doesn't really win you anything, right? So you might be better off using other stuff. So my claim would be this is very well suited for the study of flows in general. It could be flows of packets or information. For edge features, you can certainly try, but you could try other things too.
Santi, can I inject a quick question?
Certainly.
Does your framework generalize to quartets and quintuplets? Because one would expect from pairs to triplets to. Have you thought about it? Whether you can. And that's one question. And the second question is, as you climb the higher order, you observe that you need more training samples to capture the learning, the function that learned, that you learned.
Thanks. I mean that goes to the core of many of these works. So the framework that we discussed here, yes, indeed, it generalizes, and one can write it in general from signals in the J dimension to signals in the L dimension and define these kind of properties. The thing, you know, when we looked at implementations or applications of this, it's not too easy to think about what are good applications of, you know, information in tetrahedra, and then where the domain goes to the fifth dimension, right? So we actually ended up talking about, you know, flows in planes or flows in, you know, in R2 in general with holes, just because we found more applications of that. And I actually see that as, you know, all of the works that I mentioned, and I might be missing something, but most of the works at least end up focusing in the low side of the dimension spectrum, not only nodes, but maybe nodes, edges, triangles, and that's it. So I think, and as I was saying, why this is at the core of this is that to push a lot of these things, it would be nice to start to think about reasonable implementations that go beyond, you know, dimension 2, and so that we can show that this more general framework actually has lots to offer. Yeah, we don't know really what that is. Yeah.
Thank you.
Thank you.
All right. So, well, I see no further questions in the chats or in the from the meetings. So I guess we can call this. So we can conclude the presentation today. And so please join me to thank Professor Zagara again for giving a really nice talk. And we are and hopefully see you guys soon for the next Zagara seminar series.
Thank you.
Thank you very much.
Thank you. Thank you.